Hello everybody and welcome to my second video. This video is on stoichiometry. We're going to be exploring a lot of topics throughout this video, including molar ratios, converting mass to grams to moles, and a whole slew of different conversions using all the tools that we have learned so far on this journey. So stick around, we have a lot to get into. We are first going to start with molar ratios. So let's start with our discussion on molar ratios. And this is actually something that we have already seen before, but now we're going to be seeing into a kind of a new light. Where we've seen this before is when we were talking about something like, let's take N2O. And we talked about that every time that I have this molecule, which looks something like this, roughly like that. When I have this molecule, for every 2 moles of nitrogen that there's 1 mole of N2O. Every time that I have this molecule once, I have 2 atoms of nitrogen. And so we've seen these types of ratios before. And now we're going to see it in a different light. We've also seen these with hydrates, bringing back to hydrates. When I have something like, let's just say CaCl2, that 2H2O, this is the same thing as saying, there we go. This is the same thing as saying, oh, I have calcium chloride, so it's 1 of these and 2 of those, and I have 2 water molecules. And it's a ratio. It's a count. For every single time that I have calcium chloride, I have 2 molecules of water. And so this is not necessarily a new type of ratio, but we're going to be seeing it in a different way. We're going to be seeing it in terms of a chemical reaction. So let's get into an example that I've used in the past, but now we're going to look at it in terms of a chemical reaction. So we've seen this example before, talking about hamburgers, talking about buns and patties and such. And so we can say reaction like this, and you notice that I've started to use terminology and structure that looks like a chemical reaction. We have our plus signs, we have our arrows. And we could write this out. Let's just say we could write it out like this. 2 buns plus 1 patty is equal to, or I guess it goes into, 1 hamburger. And so already we kind of have a chemical equation set up. So this is something that we can make into a chemical equation here. Every time that I have 2 buns and 1 patty, I get 1 hamburger. So I kind of rewrote this, made it look a little bit nicer here. But we have this idea that I have a ratio. 2 of this to 1 of this to 1 of this. And we can think about this equation in terms of dozens, in terms of moles, because when we're counting things, it's always in the same ratio. Every time that I have 2 buns, I will have 1 patty. Every time I have 4 buns, I would have 2 patties. If I have 2 dozen buns, I have 1 dozen patties. It's the same ratio. It's always doubled. And this holds true for moles, because remember, a mole is just a really, really big dozen. It's a big number. If I have 1 mole of patties, I will have 2 moles of buns. And we see this in a conversion factor that we can do as well. We can make this into a conversion factor. And this conversion factor comes from the coefficients of my equation, we'll call it. This 2 becomes this 2. My 1 hamburger becomes this 1 here. And like any conversion factor that we have worked with, we can flip it. Every 2 moles of buns, I will have 1 mole of hamburgers. Every 1 mole of hamburgers, I'd have 2 buns. It's always the same ratio. Anytime we have a conversion factor, we can flip them. Okay? So, making sure that we can fit everything up here. Webcam is gone. Let's now take a real chemical equation and relate it to this topic that we've just talked about. So we have this chemical equation. We have 2 atoms of sodium plus 1 atom of sulfur, creating sodium sulfide. looks like up this right here. And I've split this up to kind of show you these types of ratios. We can make conversion factors out of this equation as well. Now remember, when we have an equation, we don't write in ones as our coefficients. They're not commonly written, but they are there, so just keep that in mind. And just like here's our two buns, here's our one patty, and here's our hamburger. It's that same idea that for every 2 atoms of sodium, I will have one formula units, technically molecule, of sodium sulfide. So because it's that same ratio, 2 moles of sodium, 1 mole of sodium sulfide, it's always 2 to 1, just like the hamburger. And we can then create conversion factors out of this. And what we end up finding is that the coefficients in a chemical equation can be used to create conversion factors between moles of different compounds. And this is used when we have a chemical equation. So now we've been dealing with a lot of just one-off conversions. But now we're going to start doing chemical reactions and taking their equations and comparing those values. And that's the final step that we need to get ready for stoichiometry. So let's look at some of these examples about how we can use this coefficients to convert moles. So let's start with this equation here. And for this equation, what we're going to first do is visualize what this reaction actually looks like. We have 2 reactants and 2 products. This is a single replacement reaction between aluminum and hydrochloric acid. Aluminum and hydrogen swap places. But let's break this reaction apart. We have 2 atoms of aluminum, and what I'm going to do here, I'm going to write out my atoms of aluminum like this. Plus, we have 6 molecules of HCl. Now we can simplify this to look like this. And this is then going to be converted into 2, we'll call them molecules. Technically, it's, I've said this kind of before. It's a ionic compound, it's a formula unit. And lastly, we have hydrogen. And something like this helps us visualize the conservation of mass, which is something we talked about when we were balancing equations in the first place. And what we see is that not only is atoms conserved, but mass is conserved. And we're going to see that when we start doing some stoichiometric calculations and seeing that. But what is important for us to just understand right here is when we're talking about ratios, every time that I have 2 aluminum, that is equal to 3 H2. That is the ratio of this reaction. Think of it like our hamburgers and our patties and our buns, but now the numbers are a little bit different. This means that for every time that I have, aluminum, I will have the same amount of aluminum chlorides, AlCO3s. The number of distinct molecules or atoms or formula units or whatever it is. So 2 aluminums will equal 3 H2s. 2 dozen aluminums will equal 3 dozen H2s. 2 moles of aluminum will equal 3 moles of H2. And where does this come from? The coefficient. So, with this in mind, we can then create conversion factors. So I'm going to show us one of these examples. So let's start our discussion by looking at this chemical reaction and creating molar conversion factors. Okay? What we have to look at are the coefficients here. And this is why balancing becomes an important skill, because our reaction has to be properly balanced in order to create those ratios. So our first one is between aluminum and aluminum chloride. And simply enough, we have a 2 here, a 2 here. So therefore, 2 moles of aluminum is equal to 2 moles of AlCl3. And we can use this in our reactions to do conversions, because we can say, hey, 2 moles of Al for every 2 moles of aluminum chloride. And this makes sense. Every single time that we are using aluminum, we'll have the same amount of aluminum chloride, counting-wise. Definitely not mass-wise, but definitely counting-wise. Okay? Let's see between HCl and AlCl3. We again have to look at our conversion factors, or the coefficients, to make our conversion factors. For every 6 moles of HCl, I will have 2 moles of AlCl3. For every 6 molecules of HCl, I have 2 formula units of AlCl3. It's in that same ratio. So therefore, when we're making conversion factors, we can set it up like this. 2 moles of AlCl3. Additionally, because it's a conversion factor, we can flip it. 2 moles of AlCl3 for every 6 moles of HCl. And when we are going to be doing conversions in a second, we are then able to flip this conversion factor depending on what is necessary. We're matching up units again. And I mentioned this in my last video. When we're comparing apples to oranges, we have to label what compound or atom that we are mentioning. And that's going to become very apparent throughout the rest of this video. Alright? Just lastly, between H2 and AlCl3, we would have something like this. 3 moles of H2 is equal to 2 moles of AlCl3. And that gives us our conversion factors. So now, with this in mind, how can we use these conversion factors to start converting between moles in a chemical reaction? So let's start by looking at some easy conversions. We're taking the same exact chemical equation, but this time we're going to be converting between moles. Let's think about it like this. If I have 2.4 dozen aluminum atoms, how many dozen aluminum chlorides am I going to have? Just like we've talked about, what we're looking for are the coefficients. Whenever we are converting between moles and moles, we have to look at our coefficients of our chemical reaction. So if I'm starting with 2.4 moles of aluminum, and I want to convert that into moles of AlCl3. Just like with every dimensional analysis problem that we've kind of looked at so far, the units has to match. I want moles of aluminum to be on the bottom, and I want moles of AlCl3 to be on the top. And this is where it's important to keep track of our molecules. Because of what we just talked about, the coefficients are what give us this ratio here. I have 2 moles of aluminum for every 2 moles of aluminum chloride. And mathematically, 2 divided by 2 cancels out. I'm left with 2.4 moles. What is my unit? My unit is moles of aluminum chloride. If we look at our colors here, moles of aluminum, moles of aluminum. Moles of aluminum chloride becomes a different unit altogether. It's like comparing apples and oranges. We cannot compare the two. Yes, I have moles and moles, but they're moles of 2 different things. And we have to make sure that we are keeping track of what thing we need. And that's one of the things that we need to pay attention to. If we take our second question here, if I have 0.044 moles of HCl, how many moles of AlCl will I produce? Again, we're starting with 0.044 moles of HCl. And that is our starting unit. It's not just moles, it's moles of HCl. And the more that we label this, the more familiar we are going to become with keeping track of our units, and they're less likely to make mistakes here. And I'm overdoing this, and I want you to do this as well, so that you keep track of everything. It is much, much easier to keep track of everything if you label the specific compound that we're dealing with. Because my next step, I want to convert this into moles of AlCl3. And just like anything before, moles of HCl becomes my denominator. So we set this up so that when I cancel all this out, moles of HCl goes here, moles of HCl goes here, they cancel each other out. My unit that I'm left with is moles of AlCl3. So what numbers go into this ratio here? That's again where our coefficients come in. The coefficient for AlCl3 is a 2. The coefficient for HCl is 6. Oh, let's make that a little bit more 6 looking like 6. And that is how we're going to get this. So let's pull up our calculator here. That gives me my final answer. Let's work about sake figs. We started out with 2 significant figures, so my answer here should be 0.0015 moles of AlCl3. Okay? So, what I want you to do, I want you to take a second and try out the last question here. If I produce 3.2 moles of H2, how many moles of AlCl3 is also produced? So, take a few seconds, pause the video, and when you have unpaused, the answer should be up there. So, give you a second. And there you have it. There is our answer. Check your work. Look, we have a weird ratio here. Every 2 moles of AlCl3, I get 3 moles of H2. That's not something where it's like, oh, just double it. It's a 2/3ing of it. And it's important to write it out like this because you're going to see weird ratios like this. It's not always going to be doubling it or dividing, 3 times as much of this. We have actually reached a point where everything else in this video builds upon the skills that we have learned so far. So everything from the last video that I had posted, talking about molar masses, converting between grams and moles and grams, and now the molar ratios and concentration, those are all the skills that we need to be able to do to then tackle what is known as stoichiometry. We don't need any more individual skills, but we need to be able to recognize what paths I need to take to answer questions. I am going from what to what to what. How do I get from point A to point B? There might be something in the middle. We've looked at this before when we're talking about atoms and molecules and such. There's multiple paths to get to our final answer. Or there's one path that has multiple branching paths. Let's put it that way. There's different ways to go about doing it. So what I want to start with now is just a recap of some of the tools that we have seen so far and when they are used and why they're used that way. Okay? So up here now are kind of the 4 main tools that we have worked on. Now Avogadro's number is a number 6.022 times 10 to the 23rd. And this number right here is used when we're talking about converting between anything, a count of something, and a mole. So it's 6.022 times 10 to the 23rd of anything is equal to 1 mole of it. And we don't end up using this very often. But when do I use this? I use this when I'm asking for how many atoms are there, or how many molecules are there. Anytime that we are dealing with a mass and a weight, we don't use Avogadro's number. So realistically, we don't actually end up using it often. And the reason why is because it's such a massive number. We can tangibly measure out things like mass. We don't have to count every single atom. We can just use moles. It's a nice, even, nice number. So unless I'm asking specifically for how many atoms there are, or that's part of it, you don't have to use Avogadro's number or molecules or something like that. So most of these questions, and I think every single question that follows in this part of this this video is not going to use Avogadro's number. Instead, we're going to be using the three tools here. We're going to be using concentration, molar masses, and the molar ratios that we just talked about. So let's recap what each one of these is. A molar mass, if we sound it out, a molar mass is the mass of a mole. So what this is, it is the mass in grams of 1 mole of some compound. Okay, refer to my previous video if you want to calculate it. How do I calculate it? But let's just take, for example, water. The molar mass of water is 18.02 grams per mole. So what does this mean? This means that when we're talking about weight and we're talking about moles, we can convert between the two. If I have 18.02 grams of water, that is equal to 1 mole of water. And there's our conversion factor. And like any conversion factor, we can flip this depending on what we need to convert from and convert to. So when do I use molar mass? Anytime that I need to convert between moles to grams or grams to moles. It's in the name, molar mass. If I have to go from moles to grams or grams to moles, I have to use the molar mass. And that is something that you have to be able to recognize. Okay? Our next thing is concentration. And the wordage around concentration is going to be specific. So the concentration formula, the molarity of something is equal to the number of moles divided by the volume. The number of moles of what? Of whatever the compound is. So our whatever we have that is aqueous. So aqueous moles over liters, or water liters. Water liters. And it has to be moles per liter. So whenever you get some kind of value that's in, say, grams, it has to be converted to moles. You must have moles and you must have liters. And we can use this for any type of question that's asking you to calculate any of these. I can calculate moles. I can calculate concentration. I can calculate water. Where this is going to be related to stoichiometry, and I'm going to get to what stoichiometry is once I'm done explaining this, is if I have, let's say, a given concentration, if I have 0.5 molars of something, I can calculate the number of moles of it. If I have 0.5 molar here, and I have, let's just say, 1 liter, then I would have 0.5 moles. Just doing some calculations and such. And once I have moles of something, I can convert that into grams. I can convert that into moles of something else. Number 4 right there, what we just talked about. Once I get those numbers, I can use it to convert between anything else. So what am I looking for here? What is kind of my big conversions? Well, one is that anytime I ask for concentration, it's a big one. Anytime that I ask you for volume, it's going to be probably dealing with concentration. Or anytime that I'm dealing with moles of something that's aqueous. Because we can't really count, mass out an aqueous solution. Why? Because, well, it's got water. That's got a lot of mass. But anytime that we need to find the moles of something that's aqueous, we can use concentration. And then we can do more with that with that number. We can convert it into grams, how many grams were used to dissolve for something, or as we're about to see, we can convert that into moles of an equation, which brings us to our last bit, number 4 here. What is the molar ratio? It uses the coefficient. And this compares the number of molecules of each and every reactant or products in a chemical reaction. So when do I use a molar ratio? When do I use coefficients? Anytime that we are converting from moles of, let's just call it X or something, into moles of something else. Y, it just means anything. And this is going to take place with our chemical reactions, with our using our chemical equations. So using our chemical equations. Okay? And this toolbox, these 4 things, really mostly 3 things. Molar mass concentration and molar ratios. So we're not going to use Avogadro's number that much. Are going to be utilized in a whole bunch of different ways to give us our final answers. It should just be noted as well, if I'm going to kind of go out and just review one final thing here, I've mentioned this a lot too. You also need to know conversions and watching units. So, our units of this for Avogadro's number is going to be, usually it's going to be atoms per mole, which is why it's 6.022. It's a big, big number. Anytime you're counting atoms or individual number of molecules, that's when we use this. Molar mass is always going to be grams per mole. So anytime that you have given a value in kilograms or grams, you have to convert it to match this unit. I already kind of talked about moles per liter for molarity. You have to be in liters, and you're going to get a lot of questions that will give you things in milliliters as an example. Okay. With molar ratios, it just has to be in moles, not grams. You can't compare 5 grams of apples to 5 grams of bananas. That does not work because they are 2 different things. They weigh different. Okay, I'll put this up here just as a thing that you gotta just memorize. Anytime that we have milligrams, 1,000 milligrams is equal to 1 gram. This also works for milliliters. It's 1 liter. And 1,000 grams equals 1 kilogram. I'm having you memorize them because they're the most commonly used prefixes that we're going to be seeing throughout the rest of this class. Okay? So, now what we're going to transition into is starting to look at multi-step problems and starting to build pathways. And we're going to be layering and layering up more and more and more. Along the way, we're going to be talking about what is a limiting and an excess reactant, and then we'll make a short little pit stop to talk about percent yield. And through all of that, we're going to get to some word problems that are going to really start integrating a lot that we've learned this year. So let's get to it. So before we get into some more problems, what is this word? Stoichiometry. It is kind of an infamous word when it comes to chemistry. It's one of those things that people just seem to love or seem to hate. It is my job, so I kind of do love it, to be honest. And I hope that if you do it enough, it kind of starts to make sense, and it can get kind of neat. And so here's our literal definition of this term, and this is how you pronounce it.
Stoichiometry.
Now look at that, stoichiometry. The relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically a ratio of whole integers. Or if we look at our Wikipedia ratio here, stoichiometry is the relationship between the masses of reactants and products before, during, and following chemical reactions. So, in simple terms, stoichiometry is the way that we can measure out how much of a chemical reaction I start with and how much of my products I should get. And think about it like this. If you are doing a chemical reaction, or let's say you're baking, and you have a recipe that you want to follow, and the recipe will yield 8 cookies, let's just say. You have to know how much of my reactants, my ingredients, that I need in order to get to 8 cookies. You don't want to end up with too much dough and you have extra cookies, or you don't want to have not enough ingredients and you end up with not enough cookies. You don't want to have, too little of one ingredient, because then you're not going to have good cookies. And we can think of it like baking in this example. I want to be able to predict how much of my product I should get in a chemical reaction. And any time that a chemist has to do something like this, and they have to produce something, and there's, thousands and thousands of industrial reactions and yields going on, every second across the world. All those chemicals that we use every single day. Anything that has to be formulated, from medicine to perfumes to food additives, anytime that we have some kind of thing being created, we have to know what ingredients I need to make it and how much I'm going to get. So let's look back at this equation. And let's just look at it in with what we talked about earlier. Comparing the aluminum and the aluminum chloride here. Now, if I have 2 atoms of aluminum, which is what I have every time that this reaction takes place, it uses 2 atoms of aluminum, and I end up forming 2 AlCl3s. Okay? Numerically, I will end up with the same amount of them. I'll have 2 moles of aluminum for every time I do this reaction. I'll have 2 moles of aluminum chloride. Numerically and counting. But I hope it's obvious that the mass is not the same. So the moles would be the same, but the mass is different. And it hopefully should be obvious why the mass is different, because aluminum chloride's got 3 atoms of chlorine attached to it. So the mass of this is a lot less than the mass of this. It's like the mass of an apple versus the mass of a watermelon. Or I guess in this case, it's the mass of an apple with 3 potatoes attached to it or something like that. So even though I have the same number of them, the mass is different. So if I wanted to do this reaction, and I wanted to produce how many grams of aluminum chloride I would produce, if I started with 5 grams of aluminum, I am not going to get 5 grams of aluminum chloride, because aluminum chloride's heavier, and we would expect that I would get a lot less than that. And so what we're going to end up doing, if I wanted to figure out how many grams of aluminum chloride that I end up with, I have to go about a roundabout way to do it. So instead of going from grams of aluminum to grams of AlCl3, I cannot do that, because I don't have a way to compare their masses. I don't have a way to compare between apples and watermelons. But what I do have a way to compare about, comparing aluminum and aluminum chloride, is that the moles are the same. And so I can go from moles of aluminum into moles of AlCl3. I can do that, because I know that every time I do this, I'll have the same number, the same moles. And I hope you can start to see now how I can finish off this path, because I can go from grams to moles. Think back to the toolbox. I can go from grams to mole. I need a molar mass. I can go from moles to grams. I need a molar mass. And I need this molar mass, I need that molar mass. And that's the path that we're going to be taking in stoichiometry. That's kind of the classic example, going from grams to grams. We're going to be introducing, concentration. So remember we said that concentration, another piece of our toolbox, when we have, moles over liters. If I have the concentration, I can go to moles of aluminum. So I can go from this step. I could put this into a concentration as well, depending on what I want. We start to see how those toolbox, those three things start to get used between concentration. Oh, my arrow got a little cut off. Between concentration, between the molar ratios, which I just talked about, and between mass. And that's what stoichiometry is all about. It's about understanding how do I get from point A to point B, and what conversion factors do I need to use to do it. So we're going to start relatively simple. We're going to start by just doing kind of two-step problems where we're going to introduce, let's just say, I'm going to put this in pink, we're going to do the first parts of this, like so, or from moles here into grams. We're going to start adding more and more steps, and then we're going to increase the level of complexity throughout the rest of this video. So let's get into these two parts now. Alright, so we're now at our first two-step process here. And our question that we're asking is asking us to calculate the number of moles of sodium azide is the name of this, NaN3, given two different reactants. And we're going to count this as two different questions here. So we're going to have question 1, question 2. And you're given the reaction here. Sometimes I'll have you write out the whole reactions. Sometimes I'll just ask you to balance it. Probably ask you to balance it. But here's our balanced reaction between sodium and nitrogen here. Okay. Let's look at what I am asking for. I want to end up with my final product being moles of NaN3. And my starting value is grams of sodium. There is no direct path between grams of sodium and moles of NaN3. It's like trying to compare, how many apples I have with the weight of watermelons. I guess it would be the, vice versa, whatever it ends up being. We're comparing two different things here. But path-wise, I'm starting out with grams of sodium, and I need to end up with moles of NaN3. And I cannot directly go there, so I have to go a little bit of a roundabout way. And the majority of this time, I spent a lot of time at the beginning of this video talking about it, we can convert from moles of Na into moles of NaN3. That's what we use our coefficients for. So if I can go from moles of Na into moles of NaN3, I'm just missing one more step. Grams of Na to moles of Na. And so in this type of question, from our toolbox of stoichiometry, we have two things that we need. We're going from grams to moles, so we need a molar mass. Going from moles to moles, so we need coefficients. And with this path that is now created, now I can go about and set this up. So let's do our first step. I'm going to clean this screen off and get started on it. My first step was to go from grams of Na to moles of Na. That's our first step. So I can do this by using a molar mass. Now at this point in time, please review how to get a molar mass. You can refer to my previous video or previous other videos and work. I'm going to be skipping a lot of the molar masses here, how to find them. Okay? 22.99 grams of Na for every 1 mole of Na. And please, I ask you in my class to use 2 decimal places, so please don't use 22.990. You will get the same answer in this case, but rounding wise, you'll get different answers if we use, for example, the very next example. Okay? So, This now has converted between grams of Na and moles of Na. And the unit that I currently have is moles of sodium. So my second step, and I'm going to start color coordinating this, is to then go from moles of Na into moles of NaN3. And when we're looking at our toolbox here, this is when I need a molar mass because I'm going from grams to moles. And when I'm going from moles of something to moles of something else, I use my coefficients. So I add this in. My top unit is moles of sodium, so my bottom unit should be moles of sodium. I'm trying to convert this into moles of NaN3. And like I said, when we do a molar ratio like this, we are looking at our coefficients. We have a 2 here, a 2 here. And yes, this does equal, 1, and it does cancel out. But we're at least mathematically proving it here. Watch, keeping track of my units, moles of sodium, moles of sodium. And if I put this into the calculator, and our final answer is, we have 3 sig figs, 0.329 moles of NaN3. And there is our final answer. So, I'm going to start talking about the second question right now. What I'm going to do, I'm going to set us up, and then I'm going to, just like last time, kind of poof onto the screen there. So if you want to try to tackle this question without me starting, without anything there, without talking about it, pause the video now, and you can check and make sure, check your work, see how you're doing with it. My second example here is 10.5 grams of N2. And with this example, we're similar to our other example. We're going from grams of something into moles of something to the moles of the other thing. I cannot go from grams of N2 into moles of NaN3 because they're two different compounds. There's no molar mass ratio. Molar mass has to be with the same compound. So instead, I have to go that roundabout way and go into moles of N2, and then I can go into moles of NaN3. So that is my path that I need to take. And just like last time, instead of grams of Na, I can even just cross this out. Grams of N2 into moles of N2, moles of N2 into moles of NaN3. It follows the same path. But as we're about to see, the numbers are going to be a lot different. So at this time, I'm going to let you try this on your own. And when I come back in a few seconds, answer's going to be popped up on the screen. Alright? Alright, so check your work. Your answer should be 0.250 moles of sodium azide, NaN3. Please also note I did make a mistake with my calculator. I forgot an extra 9 on there. Sometimes the online calculator is a little finicky and doesn't like to register my keys. So that should be 0.328 moles of NaN3. Alright. So, let's now talk about something called a limiting reactant. So, let's start this conversation by talking more about hamburgers. Just to recap what our reaction was when we were talking about hamburgers, we said that if we have, 2 buns plus 1 patty equal to 1 hamburger, right? And we have a very, very extreme example here. Let's say we have some kind of ordering error, and I end up with 2,000 buns but only 5 hamburger patties. How many hamburgers can I make? Well, I can only make 5 hamburgers. I'm going to have a ton of leftover buns. I'm limited to how many hamburgers I can make by how many patties I have. Because if I had a billion hamburger patties, then how many hamburgers I make with all the buns? 2,000 buns multiplied by 2 buns per 1 burger. I could make 1,000 burgers with all those buns. But I cannot do that because I'm going to run out of patties. I only have 5. So looking at this value here, if I have 5 patties, and every hamburger takes 1 of them, so 1 patty for 1 burger, I'm only going to get 5 hamburgers. Okay? So this idea of a limiting reactant is basically saying if I have 2 reactants, I have to make sure that I don't run out of them. One of my reactants will most likely run out first. I'll have it in excess. So in this extreme example, my buns, they're called the excess reactant because I'm going to end up with only 5 hamburgers. I'm not going to get to 1,000 burgers because I don't have enough patties. And so in this instance, we call the patties the limiting reactant. Okay? And this is important for us to be able to control, what I want to get out of it. The way that we can figure out which one is the limiting reactant and which one is the excess reactant is simply just by looking at whichever produces less product. And in cases where there's more than one product, it doesn't matter which product you choose. We only have one product here, which is burgers. So if I have this starting amount, how many burgers am I going to get? I'm not going to get to 1,000. I'm only going to get 5. And so when we're doing calculations with stoichiometry later, and you just saw that example where I had 2 different starting amounts of 2 different reactants, we have to base our final amount depending on whichever value we get that's lower. My excess reactant does not used up. It's not an actual yield that we can get. We cannot get to the 1,000 burgers. So with that out of the way, let's look at this example again. So in this example, if I start with those starting amounts of my 2 reactants, 7.54 grams of sodium and 10.5 grams of nitrogen, I can only produce a maximum of 0.250 moles of NaN3. I cannot create the full 3.328 moles of NaN3 because I'm going to run out of nitrogen. All of the nitrogen is going to run out before I can get to that maximum amount. So when we talk about our limiting and our excess reactants here, the N2 is our limiting. And we know that it's limiting because it produces less of our product. Alright, and in cases where there's more than one product, it doesn't matter which product you choose because the mass should mostly be the same anyways. So if our N2 is our limiting, then our Na, we would call this the excess. And that word excess just basically means there's going to be some of it left over. So we could think about this in an extreme example of a chemical reaction. If I throw a piece of aluminum into an entire pool's worth of hydrochloric acid, the aluminum's going to run out first. All of that hydrochloric acid cannot react because you just run out of aluminum. So the hydrochloric acid is the excess reactant. The sodium or the aluminum is the limiting. It limits how much of your product you can get. And so for these examples that we're going to see, when I'm asking for a limiting reactant, it's going to be whichever reactant produces, theoretically, less of your product. And I say theoretically because we're going to get into examples where even if you expect to get 1/4 of a mole of NaN3, you're not going to get that much. because that's just kind of how things are. They're not perfect. All right. So what we're going to work on next is adding another layer to this. We're going to look at some questions where we're still doing these two-step type problems before we get to the big three. All right. So let's look at another example here, where now I'm giving us a final amount. Let's say this is how much I produced of my singular product. We're still looking at the same reaction here, but I want to know how much of my reactants were used to form this amount. Now this is assuming, let's say, I don't want to eliminate reactant. I want to have an exact amount of my product. How much of each do I need? I don't have to find a limiting reactant here. Okay, remember, limiting reactants only for reactants. I'm not comparing that, I'm saying this is how much product I got, how much was used for this. And that's the thing about a lot of this stoichiometry, is that it does not just have to go from reactants to products. It can go from products to reactants. It could go from a reactant to a reactant. All right, let's say, like you're saying, I want to produce this amount. How much do I need? Think about it again in terms of baking. If I want to make 10 cookies, how much butter, how much milk, how much of this do I need in order to create this amount of cookies? That's the same line of thinking here. So when we start here, we're going to start with our path, and we're starting with milligrams of NaN3. And that is our starting path. And we want to end up with moles of Na. That is our ending path, our ending goal. Again, we can't do this conversion one-on-one. But if we start to think about this and start to take into account what we've been working on, we know that we can always go from moles of NaN3 to moles of Na. We have that relationship because we have a chemical reaction here. Because we have a reaction and because we have these coefficients. But we cannot yet go from milligrams of NaN3 to moles of NaN3. Because every time that I talked about my toolbox, I talked about a molar mass. And the unit of a molar mass is grams per mole. That's not grams, that is milligrams. So you have to be careful, and you have to know that that has to be converted. So I first have to go into grams of NaN3, and then I can use my molar mass to be a bridge between grams and moles. And note, what molar mass do I need? The last time we needed the molar mass of sodium. But when we're going from grams of NaN3 into moles of NaN3, we have to use the molar mass of NaN3. So whenever you're going from grams of something to moles of something, whatever that thing is, whatever that compound is, that's the molar mass that you need. So let's start this up here. We're starting with 549.1 milligrams of NaN3. And we first have to convert this into grams, and 1,000 milligrams is 1 gram. That gets rid of my milligrams. Alright, good. We're now in units of grams. We have to find the molar mass of NaN3. And now we can take that value that we just found, plug that in, 65.02 grams per 1 mole of NaN3. And here's where I want to make sure that I am labeling my units. I know I didn't do it for the grams and milligrams, but I want to keep track of my units. So I'm going to change colors here to show us grams of NaN3, and we have the grams here. Now I'm in moles of NaN3, and I want to go from moles of NaN3 to moles of Na. Whenever we're going from moles to moles, we have to use, I hope you can fill in my blank, coefficients. Our coefficients in this case are both 2, which makes our lives pretty nice mathematically. 2 moles of NaN3 for 2 moles of Na. And we're going to plug all of this into our calculator. And there is my final answer, which we can write out here. 0.00, what do we have? 4 sig figs. 8445. Moles of Na. Okay? So just like last time here, what I'm going to do here, I'm going to get you started on the nitrogen one. Try it on your own. Pause the video. Once you come up, the whole thing's going to be on there. Okay? Same idea. Okay, there it is. 0.01267 moles of N2. And you may have noticed a lot of similarities between these two parts. Almost everything is exactly the same except for my molar conversions. Except for this last step that I've just circled there, everything else is the same. Which is kind of crazy, right? Everything that I'm putting here in this green color, this is exactly the same. Because we're just doing a conversion into moles of NaN3. That doesn't change. What changes is what final moles I convert to. Okay? So these are the two-step questions. The next step for us is to then transition into the three-step types of questions. Where now, instead of ending out with moles here, because again, this doesn't really help me, moles of Na, that's not something I can really help. So our last part of this puzzle is to finish it off and go from moles into grams again. We're going to just go from grams of one thing into grams of the other thing. And that's going to be our next stoichiometric experience. Alright, magic of a new day of recording. Got a new camera angle, new shirt, different time of the day. Let's get into this. This problem right here represents kind of the core type of question that we're going to see in the stoichiometry, where we have two different reactants and we're trying to figure out what mass of my product I'm going to get. You might say, well, I have 40 grams of propane, which is C3H8, and I have 70 grams of O2. How much am I going to get of my product? And you can choose any product. We're going to choose carbon dioxide for the sake of this example. But I have 40 grams of propane, which is C3H8, and 70 grams of O2. You might be tempted just to say, well, I have less propane, so I'm going to get less carbon dioxide. But that's not necessarily true, and there's a few reasons for this. Number one is that propane is a lot heavier than oxygen, because it's got more atoms and heavier elements. But every time that I do this reaction, I need 5 times as much oxygen molecules. That's what my stoichiometry tells me. That's what my coefficients tell me. So we can't make a judgment call about which one we're going to produce less until we actually get into this. So this right here is kind of the quintessential what we're doing. We're trying to convert from grams of propane into grams of carbon dioxide. And we're going to start by looking at our path here. We want to get from grams of C3H8 into grams of CO2. We don't have a way to compare between them. If I bring back my apples, my watermelon example, if we have, 10 pounds of apples, and I say how many pounds of watermelons is that worth, you can't do that comparison. You need something else to go off of. And that something is the mole. Where if I can say every time I do this reaction, I have a ratio of molecules then I can make the comparison. If every single time that I buy watermelons and apples, it's buy 5 apples, get 2 watermelons or something like that. It says that you're trading or something like that. I need to be referring back to some kind of amount, not weight. We can't compare weight, we can compare the amount of something that we have, which is why we need moles. And we need moles of CO2 to go to grams of CO2. Anytime that we talk about moles to grams, that's where we need our molar mass. So we're going to need the molar mass right here. Molar mass of what? Molar mass of CO2. And I'm going to have to make this comparison between moles of C3H8. And I'm going from grams into moles, so again, I need a molar mass. This time, I need the molar mass of C3H8. And when I calculate both amounts of moles, we're bringing back that one thing that we talked about at the very beginning of this video, that last bit of our toolbox here, to go from moles of C3H8 to moles of C2. That's where we need our coefficients. When we're going from moles of one thing to moles of another thing, we need to use our coefficients. And there we have our path. We need 2 molar masses and 2 conversions, and we need to use our coefficients in the way. And this becomes a 3-step dimensional analysis problem. First thing that we need to find out, we're going to need the molar masses of both of those things here. So I'm going to pause, try to find these on your screen, on your own. They're going to appear up on our screen in just a second. Okay, so they're actually very close to one another, but they're off by about 0.1. So you might say, well, if my molar masses are about the same, I should be getting about the same amount, 40 grams to about, 40 grams. But again, that's not true, because when we talk about our ratio, our last step, our coefficients, we have a ratio here, 1 propane to 3 CO2s. So let's now take a look at what this calculation is going to look like. So rearrange a few things. I put our path underneath there in the blue just to show it in a different way. But let's start here. Our starting point, what we're starting with, is 40.0 grams of C3H8. And it's always important to just note writing out the units, which is grams, and the compound. Because we're going from compound A, C3H8, to compound B, CO2, we want to keep track of our compounds. And I do suggest that you label them. Our first step that we're going to be doing is grams of C3H8 to moles of C3H8. And whenever we're doing something like this, from grams to moles, that's when we need to use the molar mass, which is right here. So we're going to set this up. We have 44.11 grams of C3H8 per 1 mole of C3H8. And we can start to cancel out our units, grams of C3H8. That cancels out. So we have now done our first step. Our second step is now to go from moles of C3H8 into moles of CO2. Whenever we're going from moles of one thing into moles of another thing, this is where we need to use our coefficients. It's our, one of our toolbox pieces. Moles of one thing to moles of another thing. It's like our hamburger and our patties. So our coefficients, we have a 1 mole of C3H8, because there's our coefficient, we have a 1, for every 3 moles of CO2. And where does that come from? That comes from our coefficient right there. So we have now canceled out units of moles of C3H8 and moles of C3H8. The unit I'm left with right now is moles of CO2, but I want grams of CO2. So my final step here that I have to do, I have to convert this from moles of CO2 into grams of CO2. And anytime we go from moles to grams or vice versa, we need to use a molar mass, part of our toolbox. So let's set this up again. My molar mass is 44.01 grams per 1 mole. So 1 mole of CO2 for every 44.01 grams of CO2. And that gives me all of my dimensional analysis set up. Make my 4s look a little nicer. Third time's the charm. Now, all that I'm left with is actually doing this math and solving this. So, let me pull up my calculator and we're going to do this math. This gives me my final answer. We're going to make sure that we are using our proper sig figs. We started out here with 3 sig figs, so we're going to round this up to 120 grams of CO2. And so in this case, yes, it was 3 times as much. Our molar masses are very close. But look at that. We started with 40 grams of propane, and we produced 3 times the amount of carbon dioxide by mass. And I hope that this example shows that we can't just make these conversions. Because when we look at other examples where the molar masses are not the same, like with O2, we're going to see a big change there. We're going to see that it's not going to be in some exact ratio, especially because, look, we have a 5 and a 3. So our second step, our coefficient step, is going to be a little bit different. So what I'd like for you to do here, take a moment, pause, and write out the path that's going to be for this part 2. Now we're going from 70 grams of O2 to grams of CO2. So take a second and pause and try to write out what path you're going to see. It's going to show up on the screen in just a moment. There is our path, and you'll also notice that I have added in one other thing. I've added in the molar mass of oxygen. Because look at our first step. We need to convert from grams of O2 into moles of O2. So, how I'd like you to kind of go about this, I'm going to do this piecemeal. I'm going to set up each step of my equation one by one. So, try it each step, and then it's going to show up the next, each of the steps here. So, the first conversion to the next one. And what I'm going to do as well is I'm going to try to color coordinate this to show you how a lot of these steps are very similar to the example that I have just done. So try to write out the first conversion from grams of O2 into moles of O2. If you feel comfortable with looking at my example and you want to write out the whole thing, go about and do that. So in 1 second, we're going to see the first step up on the screen. Make sure that you use the correct O2 molar mass. It's a little bit different than the last example because we're starting out with a different compound. We're starting out with oxygen. Right? There's our first step done. Moles of grams of O2, grams of O2. Our next step, in our light green, is going to be our coefficient step. So in a second, it's going to show up on your screen. Try this one out for yourself. Make sure you use the correct coefficient. O2 has a coefficient of 5. Why? Because my coefficient of O2 is 5. So we're looking a little bit different than our first equation. But now our final step, we're going from moles of CO2 into grams of CO2. So I'll just cancel out my units with what's left. So try to fill out this one, which I'm going to have in the orange. And it's actually exactly the same. Because it's the same conversion going from moles of carbon dioxide into grams of carbon dioxide, we're just going to end up with different amounts. So the orange there is exactly the same because it's the same conversion going from moles of carbon dioxide to grams of carbon dioxide. So I'm going to solve for this one. Try to put this one into your calculator. Get a final answer. Remember your sig figs. Make sure that you are labeling with your correct units. Alright? Answer up on the screen in just a second. And look at that. 57.8 grams of carbon dioxide. So what does this mean? Let's wrap our heads around this and answer our last question. We started out with less mass of propane C3H8, and we produced a lot more carbon dioxide. We started with more oxygen, 70 grams, but we actually end up producing less carbon dioxide than the amount that we started with. And this goes to show us that we can't just trust, grams, how much we start with, because things weigh differently. Oxygen's lighter by about 12 grams per mole, and the ratio is more. You use a lot more oxygen molecules every time you do this reaction. So even though we started with more mass of O2, we end up producing less mass of CO2. So my limiting reactant here is whichever compound produces less of my final product. In this case, my limiting reactant is O2. And my excess reactant would be the propane. And when we're doing these types of calculations and we get two different answers, what this means is that I am not going to actually produce 120 grams of carbon dioxide. I can only produce 57.8. I can only produce my lower amount. Just like the example, if I have 2,000 buns and only 5 patties, I can only produce with the amount that I have. And that's the case here. I'm not going to get to 120.0 grams of carbon dioxide. I can only produce this amount. And so I will have leftover propane. If I did this reaction, I would have leftover propane. I would run out of oxygen before all of my propane runs out, and I would only get 57.8 grams of carbon dioxide. Okay? So what I'm going to put up here now, this is the stoichiometry kind of in a nutshell here. I'm going to put up another example here. I'm going to do one more, and then I'm going to let you try to find one of them. After that, we're going to increase the level of difficulty, and then we're going to talk about percent yield. All right? So let's start here with a more open type of question. If I calculate I've produced 4.5 kilograms of sodium chloride, how many grams of each of my reactants did I start with? And I give you the balanced equation here. And in a case like this, I'm asking you for the starting mass of both of my reactants. So it's a little bit different than the example that we have just done. In the example that we just did, we were starting with a mass of our reactants and going towards a final mass of our product. But now we're going in reverse. And when we're drawing our path here, we are starting with grams, or I should say kilograms, of NaCl. And our eventual goal is to get into grams of Na and grams of Cl2. So there's two parts to this question, because I'm asking for each of the reactants. And so let's start by building our path again. Anytime that we're dealing with going from grams of something to grams of something else, from mass of one thing to mass of something else, we have to use that molar intermediary. That's our intermediary, is moles of Na. Because when we have a reaction, we're comparing, two atoms of sodium to 2 formula units of sodium chloride. And that's where moles comes into play. So we need moles of Na, and in this case, we're going to need moles of CO2. But we can't go, straight from the mass of sodium chloride to the amount of moles of Na. We have to put our moles of NaCl. And in fact, we can go from moles of NaCl to both the moles of Na and the moles of Cl2. Why? Because we have coefficients here that give us that relationship. Every 2 NaCl's, there's 2 Na. Every 2 NaCl's, there's 1 Cl2. So we're almost there, from kilograms to moles, but we don't have a relationship between kilograms and moles. We have to first go into grams of NaCl, because our molar masses are measured in grams per mole. And so we have to start with that very just initial conversion away from kilograms. And so now we have our paths to go here. We have our two paths. We're going to need a few things to help us here. First thing that we're going to need molar masses. Because look, we're going from grams of NaCl to moles of NaCl. We're going from moles of Na to grams of Na, and moles of CO2 to grams of CO2. And Cl2, excuse me. Anytime we're doing those conversions, we need a molar mass. And from there, we have all of our molar masses that are necessary for this problem. So we're going to take this into two sections here. We're going to do part A, where we're going to convert our final answer into Na, and part B is going to be Cl2. All right, so let's start by converting into grams of sodium. We're starting out with 4.5 kilograms of NaCl. And what's actually nice is that we're starting out with the same amount for part B. We're starting out with the same amount. And so our initial moves are going to look the same because we don't actually branch until this step right here. We don't branch off until then. So we can set up both of our equations in the same way. Let's start by doing this conversion away from kilograms. Kilogram, 1,000 grams. Our next step, so we've done, let's kind of mark off our steps that we've done here. We have done this step right here. Now we have to go from grams of NaCl into moles of NaCl. We need our molar mass of NaCl. We have grams here on the top. That is 58.44 grams of NaCl for 1 mole of NaCl. Same exact thing right here. 58.44 grams of NaCl for 1 mole of NaCl. And now that we are in moles of NaCl, this is where we start to branch out. So what I'm going to do here, I kind of have to do a little bit of rearranging. I fear like I'm going to run out of space. So let me do that. I'm going to have up the rest of part A for us. And I'm going to walk you through where all this stuff comes from. Part B is going to be untouched, and I'm going to ask you to try to finish part B on your own. We should get a final answer of 1,800 grams of Na. You get about 1,770 if you do your math correctly. We start out with 2 sig figs, so I'm rounding up there. And I kind of tried to show us where I'm coming from here. My next step was to go from, let's start canceling out units, kilograms, grams of NaCl. I have to go from moles of NaCl to moles of Na, which uses my coefficients. In this case, they're both 2. Now that I have moles of Na, I have to use my molar mass, which is 22.99 grams per mole, and that gives me my final answer of 1,800. So try to finish off part 2 for me. Right? Try to use the same steps so that you're kind of getting into the rhythm of going through these steps and using the tools, setting it up, using the correct coefficients, the correct grams, the correct molar masses, right? After our next pause, part 2 answer will be up. And there it is. And I'm hidden now, so you can't see me. But we get a final answer of 2,700 grams of Cl2 after, again, we have 2 sig figs here. And what I like to show you with this type of calculation is that, well, 2 things. Number 1 is that we ended up with 4.5 kilograms. But we started with different amounts of each of my reactants. Because they weigh different, they're used in different stoichiometric ratios. So I started with different masses of them. The other thing that is really cool about this, and you know that you'll get this right if this happens like this, Look at my two masses. I have 1,800 and 2,700 grams. If I add those masses up, I get 4,500 grams. Interesting, because that's 4.5 kilograms, right? Now, obviously, I know that we did have to do a little bit of rounding here, but I promise you that if our rounding would still get the same thing. And why? Think back to chemical reactions. We talked about the conservation of mass. We started our reaction with 4,500 grams, and we ended our reaction with 4,500 grams. It just so happens because there's only one product. But this is another really neat way to show the conservation of mass. That if I start with this amount, I'm going to get the same exact mass that I end with. Okay, so our next problem, like I had mentioned before this, we're going to be introducing some more complexity into this. We're going to be bringing in another part of our toolbox in the name of concentration. So let's get to it. Okay, so here we have a whole bunch of different questions about the same reaction, single replacement reaction between magnesium and hydrochloric acid. The first type of question, that's something that is similar to what we've done already. There's no mention of concentration just yet. So what I'm going to do here is just say one thing about it, and then I'm going to let you solve this one on your own, just as some more practice. If you want to skip ahead, you're welcome to do so, but it's always a good idea to keep track of our problems and doing one on your own, because I'm not going to put up, all the molar masses and this and that. Okay? The first line of this question here says that suppose we have an excess amount of hydrochloric acid. What does that mean? Let's think back to 2 examples ago where we had 40 grams of propane and 70 grams of O2. In that instance, the propane was my excess reactant and my oxygen was my limiting reactant. And we had to do both calculations in order to figure out how much of my product I got. But by saying that I have an excess amount of hydrochloric acid, which is one of our reactants, I'm already telling you that the magnesium is the limiting reactant. So the amount of my product that I'm going to get is based off of the magnesium, which means that we only have to do that calculation. We're only converting magnesium into grams of H2. Okay? So, I recommend that you pause. I recommend that you do this practice problem. I'm having nothing onto the screen. No hints, tips, tricks. It's going to show up in about a second. I'd recommend you try this one. So, let's see what that answer looks like. Okay, there is my answer, 0.1246 grams of H2. I have 4 significant figures on my initial answer. Note, took my molar masses of magnesium and H2. I used my coefficients, which luckily for us was a 1 in each of them. Okay, let's get on to question 2, because now we have to start using concentration. There it is. So let's just recap concentration. Alright, our formula for concentration is the concentration in molar is equal to the number of moles divided by the volume. And we have to remember that our volume must be in moles, our N is in moles, per liter. So already I'm giving us milliliters, and we have to think in our mind immediately, bring that into liters. Alright? Let's then talk about the path. My eventual goal here is grams of MgCl2. So that's our final goal. Grams of MgCl2. And we know that when we do conversions like this, we always have to think about our hamburgers and our patties. We have to go from moles of MgCl2 into grams. Whenever we're doing a chemical reaction, we're going to need that moles somewhere along the way. And so we have to go into moles of MgCl2. And we can get moles of MgCl2 because this is a chemical reaction. We can get moles of MgCl2 from the amount of moles of HCl, which is my reactant that I'm talking about, because now we have an excess of magnesium. So that's my reactant is hydrochloric acid. But now there's no mention of mass in this problem. I want to find moles of HCl to convert it from moles of HCl to moles of MgCl2. But I don't have grams. It's not like the example before where I have to go from grams of one thing to grams of another things. But conveniently, when we look at a concentration, there it is. N is the moles of HCl. And so I can solve for the number of moles of HCl. M times V equals N. And that N is this value. And so there's no instance here where I need a molar mass of HCl. I am skipping grams. There's no mention, no necessity to have mass involved, to have grams involved. Which, if there's no mass, I don't need a molar mass. I don't need to do that conversion because moles is a part of my concentration formula. 55.55 milliliters, you should know that that's got to be converted. That gives me 0.555 liters times my concentration, which is 0.500. Therefore, I already know my moles of HCl, which is 0.02775. And I know we're starting with 3 sig figs, but when we're doing something mid-question, we're going to use our full amount. And so now, this becomes like one of those two-step equations from before. Where now that I have my starting moles of HCl, then I just have to fill in the rest of the equation. It's going to look a little bit something like this. This is our coefficient step, which we're using our coefficients up there. So we have 2 moles of HCl for every 1 mole of MgCl2. Now, though, we're going from moles of MgCl2 to grams. That's our last step there. So we're going to need a molar mass. My final answer, which is, now is when we bring back sig figs, 1.32 grams of MgCl2. And so it's important to be able to understand when I need molar masses, because some of us might have found the molar mass of HCl and just said, oh, okay, I need it. But you don't always need it. When we're talking about concentration, it's not always necessary because concentration inherently gives us moles. And we can see that in our next question too, where I start with a mass of hydrogen and I want to find the concentration of hydrochloric acid. So we are starting with grams of H2 and ending with the concentration of HCl. And remember, our formula is this for concentration. And what do I need to solve for that? Well, I already have my volume, which I'm going to go ahead and just already convert it. And I hope that the more that you do it, the more kind of automatic it becomes, dealing with million kilos. That's 0.125 liters. Right? But I need to find the moles of my solute, which in this case is hydrochloric acid. So I need to calculate the number of moles of HCl. I can't do that with grams of H2, but I can do my conversion to moles of H2, and using our stoichiometry, using our coefficients, I can go to moles of HCl, and I have the rest of the tools to then figure out my concentration. So with our toolbox and our path set, try to find this one out and figure this one out on your own. Alright, you only need 1 molar mass here. You don't need the molar mass of HCl again. You just need the molar mass of H2. So with our magic, we're going to see our answer. And voila, our answer is 39.6 molar, which if you know anything about acids, and anyone that has any chemistry fan, so that's impossible. But it's a fun project. The concentration literally cannot be that high, but that's okay. All right. Notice again here, I kind of did this step into one step right here, where I calculated my number of moles, and then I divided by my volume, really just for space saving. But it shows us now that we're looking for different things, and we have to be smart with what we're looking for. So we're going to take one final pit stop before we get into some more advanced word problems. The final pit stop that we have to talk about is something called percent yield. So let's get that up, and we're going to do some practice with that. So our last concept here is something known as percent yield, and it's something that kind of takes all of this this stoichiometry and puts into a little bit of perspective. Because when we do a chemical reaction, we are in no way guaranteed to actually get how much product we're supposed to. All of these numbers that we've been calculating so far, they are theoretical. They are if everything goes perfect. But nothing in life goes perfect, especially not with chemistry. And due to various reasons, there's never going to be 100% yield. Sometimes you might make a mistake and get a higher yield. Sometimes just certain chemical reactions may give you a side chemical reaction, especially true in organic chemistry, where things don't always work the way that you want them to work, and you end up with, not everything that you want. That's just kind of the nature of it. And the percent yield is a very quick and easy formula that just tells me how much did I get divided by how much I should have gotten, and puts it into a formula. So with this example right here, we did the propane example a few questions ago, and our theoretical yield should have been 57.8 grams. That's how many we should have gotten. But let's say we actually only got 50.0 grams of CO2. Just for whatever reason, some of the carbon dioxide escaped, or maybe there was a side reaction. A lot of times when there's an incomplete oxygen, just as an example, you'll start getting carbon monoxide. That's different than carbon dioxide. So let's say for whatever reason, we don't get the full amount. So when we're talking about this formula here, the actual yield, I'd like to say that's what you measure in the lab. So that would be, this is my actual yield. My theoretical yield is this. That's my theoretical yield. So simply put, doing these calculations, we end up with something that looks like this, and our yield would be 86.5%. Okay? There's a whole bunch of different questions on percent yield. I think it's a relatively simple concept, and the formula is relatively simple, but what is just important to note is that the theoretical yield is whatever the lower amount was. We had two different amounts. Our propane yielded 120 grams, and our oxygen yielded 57.8. And what's important to note when we're using our percent yield is that we're not using the 120. So the value for this, down here, we don't need that. That's no good to us. It doesn't do anything for us. Okay. That calculation is not actually going to happen because we're going to run out. So just please note that is different than a limiting reactant's different than a percent yield. The percent yield is based off of how much we're actually going to get from the reaction. Our theoretical is the 57.8. The 120 does nothing because it's not going to happen no matter what, because we're going to run out of oxygen. So please just understand the difference between a limiting reactant and the percent yield. When we get a yield, we always compare it to our limiting reactant, which we said was our oxygen. Okay? Alright, so let's get into some of these calculations here. You'll be given this formula in the top right on tests and quizzes. I don't expect you to memorize this, but let's look into it. When we calculate the yield here, it's our first thing. Calculating the yield is kind of our way of understanding that is what our theoretical yield is. That's when we do all the math that we've been doing this whole time. And you only get, right, the verbiage of that indicates that what we're actually getting is 4.76. We use our formula, percent yield is equal to the actual yield, which is 4.76 divided by my theoretical yield, which is 20, not 30. 23.3, and we have to multiply this by 100 to get to a percentage. So our answer, our percent yield, was 20.4%. Alright, 3 sig figs. Give me sig figs based off of your values there. So I show the next example as what happens when something can go wrong. Because realistically, something can go wrong in the lab. And here, we get a yield of 45.4, but we only expect it to be 40%. So it is possible, remember, our actual yield is what we got, which is 45.4, and our expected yield, or our theoretical yield, was 40. We have to multiply this by 100. So in this instance, we should be getting an answer that's over 100%. And that's okay. And I kind of prefaced it by saying, hey, maybe they made some mistake in this lab. And there's my answer down there on my calculator. Again, I have 3 sig figs, so we're going to have 114% yield. And that happens sometimes. Say you didn't dry your product enough and there's extra water that increases the mass or something like that. It's possible. Alright? Alright, so with those kind of just calculating percent yield, sometimes we might have to use percent yield in some other way. Let's move our calculator up here so we can see our last two problems. In this instance right here, we are given a percent yield. And we're trying to say if theoretically I should get 50 grams, what should I actually get? And this happens sometimes for, for chemical reactions, that there's an industry standard, especially with a lot of things like pharmaceuticals or something. There's just a lot of ways that you can't get 100% of your yield. And that's normal in the field of chemistry. So let's look at this equation here. We have our percent yield, which is 45%, is equal to the actual yield versus our theoretical yield. We are given the theoretical yield, which we said is 50.0 grams, and we're looking for our expected actual yield, which we don't know. We call this X. And there is that 100% here, and we should always start by tackling the 100% and turning 45% into a decimal. And we can do that pretty easily just by dividing it by 100. Mathematically, we're getting rid of, we're taking this extra step here, dividing this by 100, dividing this by 100 to get rid of that. And now we're left with 0.45 is equal to X over 50.0. We can multiply both sides of my reaction, my equation there, and that can give us our answer. So we are taking that number times 50.0, and that gives me my expected actual yield, which would be 22.5, and we do need a unit here. It is grams. 22.5 is just a number, grams. Notice I included the percent up top. All right, last one here. We're again given a percent yield right here, 57.5%. And now we're recovering 23.0 grams. That's what we actually got. So that becomes our actual yield. We're trying to find our theoretical yield. Just like last time, we're going to end up dividing by 100, and we're going to get 0.575 equals 23.0 divided by x. Okay, I've done this type of calculations a lot. You cannot multiply by x, or you cannot multiply by 23. We have to multiply by x to cancel it out. We end up getting 0.575x equals 23.0, and we can solve for this. X equals what is it? It's 23 divided by 0.575 gives me my final answer right there. We have 3 sig figs, so we should have 40.0 grams as our theoretical yield. Okay? So, let's move on to our final part of this very long video, which talks about word problems. Alright, so here we have kind of a little bit more involved of a word problem, where you're not given a chemical reaction, and we have to use some of the skills that we have learned previously in this throughout our class in order to solve this. And as you've seen before, we need an accurate chemical reaction for several things. An accurate chemical reaction is going to tell us the stoichiometric ratios, those coefficients that we need. In addition, it gives us proper formulas, which tells us what our molar masses are going to be. Alright, we have a 5.50 gram piece of zinc that is placed in a beaker with 200 milliliters of 0.05000 molar silver nitrate. This reaction will go. How much silver should you get? We have to first figure out what our limiting reactant is. Are we going to run out of zinc, or are we going to run out of our silver nitrate? So we have to do 2 stoichiometric conversions here. And now that we've set this up, this is a very similar example to ones that we have previously done. So what I'm going to do here, I'm going to do this into the background. I'm going to speed this up a little bit. We're going to play some funky music or something like that. Alright, you can always pause and review the steps that I'm doing. You know, pause, go through it, speed through it, whatever you want to do. Alright, so there is the first type of reaction done, converting our zinc into our silver. We get 18.1 grams of silver. Let's now get into our silver nitrate using our concentration formula. Okay, so doing all of this math, we converted into moles of AgNO3 and then converted that into grams of AgNO3, and we got 1.08 grams of silver. So clearly, our limiting reactant here is the silver nitrate. I will run out of silver nitrate before I run out of zinc. So I would still have my zinc floating around in my beaker there. It would not run out. I'd still have leftover of it, right? My limiting reactant becomes silver nitrate. There is our first word problem. Let's move on to the next one. Alright, so now we're moving on to a double replacement reaction. And this is quite a famous one. I think I did this one in class where we are producing a yellow precipitate. We have a spectacular double replacement reaction. First part here is to write out and balance the full equation, including states of matter. So we have to start with our chemical formulas. Let's start by writing out how much I have of each of my two reactants, because we're trying to find kilograms of precipitate. So our final goal here, let's start with our path, should be kilograms of PbI2. But I'm starting, well, even though I'm starting with the same amount of each reactant, I'm still going to get different amounts of my products because we have a different stoichiometric ratio here, okay? So our goal here, first thing, whenever we're doing these types of calculations and we're dealing with molar masses, hopefully we understand by now that we're going to be using a molar mass to get grams of PbI2. And then from here, we need to go from moles of PbI2 to grams of PbI2. We have two reactants that we need to compare. So we have to compare moles of PbNO3 into moles of PbI2 and moles of Ki into moles of PbI2. Now the thing here is that our starting amounts, because our concentration and our volume are the same. Remember, concentration is the number of moles divided by the volume. So we can rearrange this formula, N equals M times V. Conveniently, I've given you liters this time. We have 4.00 times 0.250. So our N is exactly 1.0 moles of each of my reactants is my starting point. So of both of my reactants, I have exactly 1.00 moles. And we can start to convert this. So what I'm going to do here is I'm going to start with this value that we have. We're going to start both A and B. So in a second, I'm going to do this first step right here. Alright, so I'll be right back. Alright, so I've set up my two reactants. And I actually don't need to do both of these because I started out with the same amount here. And maybe it's a little bit, some generosity here. But if we look at this amount right here, I started out with 1 mole of each of my two reactants. But I need double the amount of potassium iodide. I need 2 potassiums and 2 iodides every time I do this reaction. And so what ends up happening is if I start with 1 mole, I'm going to end up with less. We can kind of already tell that my limiting reactant is going to be Ki. Just by doing this, I'm going to end up with 1.00 moles of PbI2, and down here 0.5000 extra 0 moles of PbI2. Just already in this conversion. And think back to the very first time that I introduced limiting reactant, I actually based it off of moles. In this case, because we're starting out with moles like this, I don't have to do the rest of this. I could, but I don't have to. I already know that my limiting reactant is going to be potassium iodide. This is my limiting reactant, which means that this is not necessary. I will have excess lead nitrate. So, with this in mind, let's rewrite this, and now we're going to finish off only part B and get my answer. So, I'm going to rearrange this a little bit, make it look a little bit nicer, and we'll finish off our reaction. So, pause the video here if you would like. I'm going to be finishing off point B. You can rewind to look at the path that I need to go to get to kilograms of my precipitate. But answer is going to be up on the screen in just a second. Should get 0.231 kilograms of lead to iodide. There is my final answer. Set this up. I found the molar mass of lead iodide, 461. It's a very heavy compound. And that gives me my final answer. If you had done this, just because I understand the math here, if you did go through and you did it with the lead nitrate, you'd probably get double that. You should get double it because it's pretty much the same thing there. But doubled, you'd have a 2 up there. If you did this with the lead nitrate, you would have a 1 down here, I should say, excuse me, which basically means that you're doubling that amount. And you would still end up showing that lead iodide, you end up with 0.231 kilograms. Okay? I got one final question that I'm going to go over. So let's get to that last question. Alright, so final question is one more double replacement reaction. We're doing a single double replacement reaction between potassium chloride and silver nitrate. I do just tell you that it is solid potassium chloride. It's a little bit different than what we've done so far. Do tell you that we have an excess of potassium chloride, which means that silver nitrate becomes our limiting reactant. And I want to calculate the theoretical yield of my precipitate, which is my AgCl. Because it's a solid, because it does not dissolve, it is my precipitate. And so in an example like this, I'm asking us to know that vocabulary. And I was very, let's see, hands-off with the way that I describe this question, because you need to understand which one is my precipitate so that you're converting it to the right answer. So we want my yield of precipitate, which means that we want to end up with grams of AgCl. AgCl. And we're starting with this amount of silver nitrate. All right? So hopefully now that I've set this up, you can figure this one out on your own. So I've set this up and I've tried my best to explain it. So pause, try to solve for this question. It's going to be up on the screen in just a few seconds. And boom, there is the answer, 14.3 grams of AgCl. Please just note my molar masses. I'm not showing my work for how I'm getting these because I've done a lot of examples of these. I'd still like you to show me your work for them, especially when they're kind of simpler. Like, AgCl has only got 2 atoms in it. Makes our lives a little bit easier. We do have a 1-to-1 ratio with our coefficients, so it is a little bit of an easier calculation here. But that's what we should be getting. Okay? Last question of our marathon video here is to calculate the concentration of the remaining aqueous solution. What does that mean? When we're talking about remaining here, and framing this here, the remaining aqueous solution, we already know that silver nitrate is our limiting reactant. So when I'm asking for the remaining aqueous solution, I guess what I'm asking for is, what is the concentration of potassium nitrate? And that's how I would frame this question. All right. I also give us this information that the final volume is the same as the initial volume. And that information is going to help us here. Because this question, when we boil it down, is not very complicated. Why? Because I know that my starting value right here, I know that I have 0.100 moles of AgNO3. And if I convert this, I have 1 mole of AgNO3 for every 1 mole of KNO3. And I'm just going to get 0.100 moles of KNO3. Because what I'm asking for is the concentration. And concentration is N divided by V. So I need to find N. And I needed to find the N, the moles of KNO3, which I just found. My volume stays the same, which is 0.250. And I end up with the same exact answer. I have a 0.4 molar KNO3. Alright? Same exact answer. So let's summarize this video in one final understanding. If you made it this far. Alright, hello, look, it's me in full picture right here. Stoichiometry is one of those very hit or miss things when it comes to chemistry. I've had students say it's the death of them. I've said students, they love them. I am the type of person, I love doing it. I think it's logical. I think it's neat and organized. And I hope that part of my emphasis throughout this video is understanding the path that I need to use and how to get from point A to B to C, using dimensional analysis and using the tools that we have learned, whether it's the molar masses, whether it's using concentration, or whether it's converting between moles of one thing to moles of another thing. And throughout the rest of this year, we're going to see more instances of stoichiometry used in various different ways. We're going to talk about the relationship between mass and volumes of gases. We're going to see the relationship between pressure. We're going to see the relationship between energy. You know, if I burn this amount of carbon dioxide, how much energy do I get? And so stoichiometry is used all throughout chemistry to relate various properties. And it requires us to understand what I'm converting from and what I have to go to, and using all of those tools. I hope this video helps. It's going to be a very fun time editing all of this, but I think it's worth it because I want you to have resources to help yourself. So thank you all for watching. If you've made it this far, I'll say it. You know, most YouTubers now, they plug it in somewhere in their video. You know, smash that like button, all that fun stuff. All right, have a wonderful rest of your day. Good luck with your stoichiometry.